Okay, so I know in class things can be kind of difficult to understand with all the stuff that's going on, distractions that can occur, and sometimes it's hard to read and bored. Sometimes we move a little bit too quickly. Sometimes things just kind of get a little fuzzy, right? So hopefully the video here kind of helps explain a little bit. I can break it down and try to do it a little bit simpler. Try my best to explain the best that I can. So here today we're going to talk about chapter 3.4, which is Bayes probabilities. Now, Bayes probabilities is it's kind of like what we did in section 3.3, where we had the tree diagrams, and we found probabilities of certain events occurring by multiplying the branches of each event together. And we'll do that again here, but the difference between what we did in 3.3 versus what we're doing here is conditional probability. So conditional probability, it's important to understand how that works. We've talked about it a little bit in the past, but to give you an example of conditional probability, before we actually get into any of the Bayes probability examples, just conditional probability itself is helpful to understand. So here's how conditional probability is set. So let's say that there are 10 people in a room, right? I'm just going to draw lines for the sake of lines. I'm going to say that 6 of these people are girls and 4 of them are boys. Now, 2 of the girls have blonde hair. 3 of the girls have brunette hair, which I guess I'll just label R. I guess I should do that because I was going to say red hair next, but I guess I'll use G for red hair as ginger. All right, so B for blonde, red for brunette, G for ginger. Although I know it's not, ginger's kind of rough. Let's just go ahead and say it's man, so many hair colors that start with the letter B. I just realized. Brunette, blonde, brown. Let's just say brunette's BR. So 3 of them are brunette, and then 1 has red hair. And for the boys, let's say 1 of them is blonde, and the other 3 are brunette or brown hair. Okay, so conditional probability. Regular probability is, okay, if I'm going to choose one of these people at random, what's the probability that it would be a boy? Well, the probability that I choose a boy would be 4 out of 10. Because there's 4 boys, 10 people, 4 out of 10, right? Probability of choosing a girl would be 6 out of 10. Now, that's just normal probability. That's not conditional probability. Conditional probability is when I break it down into something further. I say, hey, if I've chosen a boy, what's the probability that he has blonde hair? Well, now I'm only focused on, how many boys there are. There are 4 of them, and only 1 of those 4 has blonde hair. So the probability would be 1 over 4 of choosing a boy that has blonde hair, given the fact I know I've chosen a boy. So conditional probability focuses on a specific event, and that event becomes like the total 100%, right? So here, instead of the 10 people, the total is now 4 people, right? And I broke it into, well, how many of those 4 people had blonde hair? And it was 1 of them. So conditional probability, just another sample. Let's say, what's the probability that if I chose a brunette, what's the probability that that brunette is a girl? So now you look at the brunettes and you go, okay, given the fact that I'm choosing a brunette, there are 1, 2, 3, 4, 5, 6 brunettes in total. How many of those brunettes are girls? 3 of them are girls, right? So the probability that you choose a brunette, they're a girl, given the fact that you know they're brunette, is 3 out of 6 or 1/2. So remember, the new standard or the new 100% value is 6. We're looking at 6 total, and how many of those 6 were girls. Okay, so it's important to keep in mind that the denominator is changing from 10 because there are 10 total people to something else, given the fact that we're focusing in on that specific event or that specific occurrence. All right, so let's look at example 1. Marvin's Music places 80% of special orders for CDs to a distributor in LA and the remainder to a distributor in New York. Special orders are always shipped a next day delivery by the distributor, but they do not always arrive the next day. Shipments from LA are late 5% of the time, and shipments to New York are late 10% of the time. If a randomly selected special order arrives on time, what's the probability that it came from LA? So first and foremost, let's go ahead and set up our tree diagram to sort of get a visual and help us better calculate some of these probabilities. So the first branch is going to be our distributors. We're either getting a package from LA or New York. Now LA, my package can either be on time or it can be late. And same thing from New York. It can come from New York, it's either going to be on time or it's going to be late. Let's fill out the probabilities of these. So 80% of the special orders come from LA. So 80% is 0.8. So that's the branch there. 80% come from LA. And that means the other 20% come from New York. So just to explain why it's 0.8 and 0.2 there. Now, if it comes from LA, shipments arrive late 5% of the time. So 5% is 0.05, not 0.5. 0.5 is 0.50 or 50%. 0.05 is 5%. So it's late 0.05, which means it's on time 0.95% of the time, or 0.95 probability. And from New York, it's late 10% of the time, which is 0.1. And so that means on time 90% of the time, which is 0.9. So now here's the conditional probability that we're focused on. We know that the package has arrived on time. So when you think back to the girl and boy example I had earlier, there was 10 people in total. And in the percentage of this problem, there's 100% at stake here, 100% in total, right? But now we're not focusing on that full 100%. We're only focusing on the percent that arrived on time. So the first thing I want to do is figure out what is the percent that arrived on time. Because that would be like saying, hey, I've chosen a person with brunette hair, then what's the probability that they're a girl? So I need to figure out how many girls had brunette hair first, or I'm sorry, how many people had brunette hair first, and then I would see how many of them were actually girls. So here we need to figure out what specifically is on time, and then we'll figure out how much of those came from LA. So for on time, there's two possibilities. There's the one from LA and the one from New York. So the one from LA, we get the probability here by multiplying the branches together. So 0.8 and 0.95. You multiply those branches together. Oops, that's supposed to be multiplication. 0.8 times 0.95. And you get 0.76. Okay, so that's the probability that it's on time and it's from LA. Now the probability it's on time and from New York, we multiply the branches of New York and on time together. So that's 0.2 times 0.9, which equals 0.18. So the total percent that it's on time is just these two added together. So 0.76 plus 0.18 is 0.94. So that's not my answer, but that's how much, that's the total value for being on time. So back to the example with the people, if I said I'm choosing a person who's brunette, and then I'm going to figure out how many of those brunettes were girls, this is me figuring out how many people are brunette. It's figuring out what's the total people that are brunette. I've just found out the total that arrived on time. So that's my given. That's my new denominator. Okay. Now that this is how many arrive on time, now I need to focus on how many of those, how much of that, I guess I should say, comes from LA. Because the question's asking, if it's on time, what's the probability it came from LA? Now the amount that came from LA is 0.76. So I have 0.76 over 0.94, and that gives me my total probability here, which is about 0.8 in total. So it arrived on time. right? My 100% is now 0.94 because that's the total percent that arrived on time. And of that 0.94 that arrived on time, 0.76 of it was LA. So 0.76 over 0.94 gives me that probability. So it's just like saying, there are 6 people with brunette hair, or I guess let's say there are 94 people with brunette hair, and 76 of them were girls. So 76 over 94 is the probability. Same idea, okay? Except it's not brunette hair and girls. It's on time and LA, okay? So keep that kind of in the back of your head. Hopefully that did a decent job explaining it. Let's do another example. Maybe it'll start to sink in a little bit more. So Clyde has a rather casual attitude towards his courses, and he studies for 1/3 of his exams selected at random. In the past, he has passed, that's tricky to say, 3/4 of his exams he has studied for, and 1/4 of those he has not studied for. So he passes 3/4 of every test he studied for, and he passes 1/4 of every test he does not study for. So given the fact that we know Clyde passed his math exam, we want to find the probability that he actually had studied for it versus whether he had not studied for it. So let's go ahead and let's make our tree diagram first. Okay, so there's 2 branches to start off with. Either he studies for the test or he doesn't study for the test. Studied versus not studied. S for studied, N for not studied. So if he studied, he has a chance of passing the test or failing the test. And same thing if he doesn't study. He either will pass the test or fail the test. So there's your other branches. Let's go ahead and fill out the probabilities. Now it says he studies for 1/3 of his exams. You can use decimals if you want to, but I think for this video, I'll go ahead and just use the fraction. Because we did decimals in class, so you should have that written down already, but I'll use fractions here just so we kind of get, best of both worlds. So he studies for 1/3 of the exams at random. So studies would be 1/3, which means he doesn't study for 2/3 of them. Now, in the past, he passed 3/4 of the exams he studied for. So if he studied, there's a 3 out of 4 chance he passes, which means there's a 1 out of 4 chance he fails. And 1/4 of those he has not studied for. So when he doesn't study, he passes 1/4 of his tests. So that means when he doesn't study, he fails 3/4 of his tests. Okay, so there's our tree diagram. Now let's start to answer the question. We know Clyde passed his math exam. So let's focus our attention on the probability of where he's passed. So if he studied and passed, that's 1/3 times 3/4, which is 3 over 12. And if he didn't study and he passed, then that is 2/3 times 1/4, which is 3 out of 12. Oh, I'm sorry, 2 out of 12. My apologies. All right. So if you add these together, then he's going to pass 5 out of 12, or 5/12 of the time. Okay, which is not very much, but there you go, 5/12. Now, what's the probability? So this is the this is the total amount that he would pass. What's the probability that he studied and passed? Now, he studied and passed 3/12 of the time. So essentially, if you want to think of this as a fraction over fraction, we know he passed the test. So we know that the new overall probability is at 5 out of 12. Right. Of that, he studied for the test 3 out of 12. Right? This is the probability he studies the test. So 3/12 divided by 5/12. If you remember anything about how this kind of works, when you divide fractions like this is really the same as 3/12 times 12/5. Now, the 12s cancel, and you can continue working this out. You can do it with decimals if you want as well. But the answer is 3/5 or 0.6. So let me go back through that problem because I feel like I didn't do it a very good justice. So what's going on here is we know Clyde passed his math exam. So the new total is 5/12 because 3/12 he passed when he studied and 2/12 he passed when he didn't study. So he passes the test 5/12. That's that probability. So this is like, back to the choosing a brunette and the chance of being a girl. There are essentially there are 5 brunettes here. And the probability of choosing a girl would be 3 out of those 5. So that's where you get the 3/5 from. The fraction up here is more of a technical thing, I suppose. But it's easier to think of it kind of like that brunette, that hair color question, in my opinion. I don't know. It's tricky. It really is. It's one of those things that really takes just a couple practice attempts on, but we'll try again. Okay. We'll see if I can't do a better job on example 3. A faculty member at GSU regularly teaches an evening course in a neighboring city. Each time he makes a trip, he randomly assigns transportation from the university motor pool. The motor pool consists of 50% Chevys, 30% Fords, and 20% Volkswagens. Some of the cars are air-conditioned, others are not. 60% of the Chevys are air-conditioned, 50% of the Fords, and 30% of the Volkswagens. One afternoon, the faculty member is assigned an air-conditioned car. What's the probability that it is a Chevy? So I'm going to kind of help teach this a little bit. I'm going to pretend that percents are out of 100, or saying that there's let's say there's 100 cars. How many of them are Chevys, Fords, and whatnot? So let's start by making our tree diagram. So there are 3 manufacturers to choose from. There's Chevys, there's Fords, and there's Volkswagens. Now, each car is either air-conditioned or it's not air-conditioned. So if there were 100 cars in total, right, 50% of them are Chevys, that would basically mean that there are 50 Chevys, right? But let's keep with the probability for now, but hopefully in terms of what we're doing, maybe the numbers that will actually make more sense than the probabilities do. 30% of them are Fords, so that would be 0.3 for Ford. And 20% of them are Volkswagens. Now, of the Chevys, 60% of the Chevys are air-conditioned. So that means 0.6 for the air-conditioned Chevys, 0.4 for the not air-conditioned Chevys. 50% of the Fords are AC'd, so 0.5 for the AC, 0.5 for the not AC. And 30% of the Volkswagens, so 0.3 for the AC, 0.7 for the not AC. So let's calculate the probabilities of each of these, then we'll answer the question. Maybe we'll try that approach here. So the probability that we have a Chevy that is AC'd is 0.5 times 0.6. And 0.5 times 0.6 is 0.3. The probability it's a Chevy that's not AC'd is 0.5 times 0.4, which equals 0.2. The probability we have a Ford that has air conditioning is 0.3 times 0.5, which is 0.15. And the probability we have a Ford that is not AC'd is 0.3 times 0.5, which is the same thing. So that would be also 0.15. The probability we have a Volkswagen that's AC'd is 0.2 times 0.3, which is let me just double check that to make sure. 0.2 times 0.3, 0.06. And the probability of a Volkswagen that has no AC is 0.2 times 0.7, which is 0.14. So basically think of this. There's 100 cars in total, right? So if you want to imagine that there's 100 cars in total, this means 30% of them are Chevy and AC. So 30 cars are Chevy and AC. 20 cars are Chevy and not AC. 15 cars are Ford and AC. 15 are Ford without AC. 6 cars are Volkswagens with AC, and 14 are Volkswagens with not AC. Okay? So conditional probability is this. So we know we have an air-conditioned car. So how many air-conditioned cars are there? There's 30 for the Chevys, there's 15 for the Fords, and there's 6 for the Volkswagens. So 30, 15, and 6 means that there are 51 cars with AC. Now again, this is probability, so it's really, 0.3, 0.15, and 0.06. So which makes this a probability of 0.51, right? But if we're thinking of out of 100 cars, then we can just think of it like this, right? There are 51.51, but really let's say 51 cars that have AC. How many of those cars are Chevys? Well, there are 30 cars that are Chevys with AC, right? So 30 of the 51 AC cars are Chevy. So there's your conditional probability, and that is whatever 30 divided by 0.5, or 30 divided by 51 is, which is, yeah, 30 divided by 0.51, or I'm sorry, 30 divided by 51, 0.588, it's almost 0.6, okay, it's about 0.59-ish, okay. So I think that helps explain it a little bit better. Converting the percents into actual numbers, I think, makes a little more sense. So I'm pretty stoked about that one. All right, let's try example 4. So I'm sorry if this video is kind of running long. I'm trying to be a little bit helpful. So there are 2 buckets, one labeled H, one labeled T. And then we're going to choose 2 balls from each bucket at random. One ball right after the other without putting it back in the bucket. So you can read the problem, but I'm kind of explaining what it says. So in the H bucket, there are yellow and white balls. So my first choice, I'll either choose, if I go in the H bucket, I'll either choose a yellow or a white ball as my first choice. And then if I chose a yellow, the second ball will either be yellow or white. If I chose white the first time, the second ball will still either be yellow or white. Now for the T bucket, T has 2 yellow and 1 white ball. So my first selection, I will either choose a yellow or a white ball. Now if I choose a yellow, there's still another yellow and still another white in that bucket. But if I chose white, there's only 1 white ball. So if I chose white, then there aren't any more white balls to choose from, and that branch would only be towards yellow. So let me do this on some place where I have a little bit more space. So let's redraw that tree. So H bucket, T bucket. H, yellow or white ball, and again, yellow or white ball. Now for T, I'll either choose a yellow or white ball, but because T only had 1 white ball, if I chose the white ball here, then that means there isn't another white ball to choose, and the only option I would have for the second ball would be yellow. So I'm flipping a coin to determine whether I choose heads or tails. So that's a 1/2 probability that I choose H, 1/2 that I choose T. Now, if I chose H had, I don't know if there's a way to minimize this. Nope. I don't remember how many H had. H had, I believe it was 3 yellow and 2 white. So there are 5 balls in total. So the probability of choosing a yellow would be 3 out of 5. The probability of choosing white would be 2 out of 5. Now, if I chose a yellow, so here's a representation of those 5 balls. Okay, I'm being lazy. I'm not choosing colors. Okay, if I chose a yellow the first time, right, and that ball's been taken out, then the probability of choosing a yellow on the second draw is 2 out of 4. And the probability of choosing white on that second draw would be 2 out of 4. Now, if I chose a white ball the first time, right, then the probability of choosing a yellow would now be 3 out of 4. And the probability of choosing a white would be 1 out of 4. Because that's how many are remaining there. Now, for the T bucket, T only had 2 yellow and 1 white. So the probability of choosing a yellow would be 2 out of 3. And the probability of choosing a white would have been 1 out of 3. Now, if I chose a yellow the first time, right, then the probability of choosing a yellow the second time would be 1 out of 2. Same thing for white, would be 1 out of 2. Now, if I chose a white the first time, the probability of choosing a yellow is guaranteed, right? Because there's no other option, I'll have to choose yellow. So we can say, 2 out of 2, 1 out of 1, but same thing, it's just going to be 1. So let's write the probabilities for each of these out. So the probability for heads, yellow, and yellow, probability for heads, yellow, and yellow is 1/2 times 3/5 times 2/4, which is 6 out of 40, which reduces to 3 out of 20. Oops. The probability of choosing a heads, yellow, and a white is the same thing, 1/2 times 3/5 times 2/4, which would still be 6 out of 40, or reduced to 3 out of 20. The probability of choosing a head, a white, and then a yellow would be 1/2 times 2/5 times 3/4, which would be 6 over 40 as well, which reduces to 3 over 20. And the probability of choosing a heads, white, and a white would be 2 out of 40, which is just 1 out of 20. The probability of choosing a tails, yellow, and a yellow would be 1/2, 2/3, and 1/2, which would be 2 over 12, which is the same as just 1/6. Probability of choosing a tails, a yellow, and a white is 1/2 times 2/3 times 1/2, which is same thing, 2/12 or 1/6. And the probability of choosing tails, white, and a yellow would be 1/2 times 1/3 times 1, which would just be 1 over 6, which is simply just 1 over 6. So if you add up all of these, this all adds up to 1. If you add up all these 3 over 20, 3 over 20, 3 over 20, 1 over 20, 1 over 6, 1 over 6, 1 over 6. Okay, they all add up to 1. But the question that we're going to answer now is, if exactly 1 white ball is drawn, what is the probability that the coin landed with a head up? Oops. Pull back my sketch pad. All right, so exactly one white ball is drawn, that's going to be, let's see, heads, yellow, white. That's going to be this probability. Heads, white, yellow. That's going to be this probability. Those both have exactly one white ball drawn. Wouldn't be this one because that doesn't have any white balls. It wouldn't be this one because that's two white balls. We're looking at exactly one white. So this probability has exactly one white, and this probability has exactly one white. So we would add up all these together, and that will be my denominator. So 3 over 20, 3 over 20, 1 over 6, and 1 over 6 would be, I'm trying to think of that all added up. Let's see. I'm thinking of the common denominator being like 60 or something. So that would mean 9, 9, 10, and 10. That's 20, 18. So it'd be like 38. Well, out of 60, what's that reduced to? Well, decimal-wise, if you add up those fractions together, you're going to get a probability value of 0.633. So that's the total probability of having exactly one white ball. Now, given the fact that it's white, how many of those are now probability that it's heads? Well, probability that it's heads would be just these added together, these two. 3 over 20, 3 over 20, which is 6 over 20. Now, if you want to just type 6 over 20, get the decimal version of that, you can. 6 divided by 20 is 0.3. So our probability would be 0.3 over 0.63, which equals something close to about 1/2. About 0.48. If you round it a little bit. So remember that the bottom part is going to be the total of the given. So, we asked for how many exactly had one white. So we had these 4 probabilities. We added them all up to see how much was the total for one white. And then we were thinking, now that we know what the total of one white is, how many of those are strictly from heads? And that would have been 3 over 20 and 3 over 20, which is 6 over 20, which gave us the 0.3 value. So the number on top is the white, exactly one white, and it was heads. And the part in the bottom is the exactly one white in total. Okay. I'm going to end it. I'm sorry if this took forever, but again, you didn't have to watch it, but I'm just trying to help. All right, I'll see you next time. Bye.